Hi guys. Sorry that we have to do it this way again today, but well, virtually always, but now virtual with a video is very strange. But hopefully we can get through this, and 7-1 will be understood well by you by the end of our lesson today. The first thing I want to do is a quick warm up from yesterday. I want you to go into Edpuzzle and give me an example of a parameter and give me an example of a statistic. And then I'd like for you to tell me what is a sampling distribution and draw a picture that would help someone visualize the definition. So first write out a definition of a sampling distribution, which we learned yesterday in our notes. And then I gave you several types of pictures and ways to see us going from the population to samples to a sampling distribution. I'd like to see you work on that, if you could, please. And then I'll come back and we'll talk about it, okay? All right, welcome back. Here's the answer key I would go through. I just made up one, so let's just see. The parameter I have is, let's say, 52%, so you should always use some number that represents the population. So 52% of MVHS seniors go to the prom. MVHS seniors is my population, and 52% is my P, the proportion, which can often be written as a percent. Okay, statistic would then be 30 MVHS seniors were surveyed, and 63% are going to the prom. So now this is a sample we took, and we got a sample statistic, which is P hat here. Okay. All right. You can check your own conditions. I'll be checking it when I look at Edpuzzle. How about your sampling distribution? This definition is important. It's the distribution of values taken by the statistic in all possible samples of the same size from the same population. Okay, very important. All those parts are there. It has to be same size samples, always taken from the same population, and then you are taking some statistic from those samples and plotting those down and causing a distribution of the statistic. Okay, I gave an example here of a little picture I drew to help someone visualize it. We used heights of 4 gentlemen yesterday. That was 4 sons of a family, but I just made 1, 2, 3, 4 to keep it easy. Here's my my population, the 4 numbers. And the mean of those 4 numbers is 2.5. Right? And this has a standard deviation of 1.12. I put in all my possible samples of size 2 and took their means, X bars, sample statistic, sample mean off each sample. And when you average those, the mean of the X bars, notice the difference. This is mean of X, my population X's. Now this is the mean of all the sample means. This is weird. Mean of the means, okay, is 2.5. And when you plot them, you will see here that it's starting to look normal, and we've reduced our variability quite a bit. Okay, and there's what happens. This is now pulling out the extremes, and we pull them in because we're averaging them. Okay, so that was just a review from yesterday's. Knowing the difference between statistic and a parameter and what a sampling distribution is. So to go further, I want you to now look at this practice of statistics and parameters. We're not doing question number 3 right now. We'll learn how to do 3 next Thursday, Friday. So just doing 1 and 2, what I want you to do is practice classifying each of the underlying numbers as either a parameter or a statistic, and please use the appropriate symbol. So in Edpuzzle, if you'd please do number 1 and number 2. It would be hard to do the symbol, so you could write X bar or mu, MYOO, I guess. You could put P hat or P. So just use some words and describe what that would be, okay? And then come back and we'll look at the answers. All right, welcome back to the answers. Hopefully you saw that Chipotle on College Avenue, which someone from our class works there. Averages 50 teenagers per day in the restaurant. So this is their parameter. This is what they average on a day-to-day basis. They say their mean, their mu, is 50. It's a parameter. But you're going to stand outside the restaurant on a given day, randomly chosen day, and you're going to count the number of teenagers entering, and you get 63. This is now your statistic, okay? Your statistic X bar, you'd say, well, actually on this day we had 63 students come in, okay? What about number 2? Mr. Ortiz ran a Google survey. Oh, a survey, that must be getting a sample that found 23% of the student body plan to attend the next dance. So this is our statistic. It's a percent, which is like a proportion, so it's p hat at 23%, and then the 15% is on the day of the dance, 15% showed up. So this is the population. This is actually what happened. 15% of MVHS student body attended. So this is our parameter, and it's a proportion. It's a percent, so that we use the P for percent proportion. Okay? All right. Enough on that one. And now we're going to go back, and I want to just finish up. Oh, dear goodness. Come back here. The notes. Okay. I want to start. I know we saw this slide yesterday, but I want to start here to just re-emphasize what we are doing here, and what you are trying to explain in your drawing to me too is that you have the population, whatever the claim is of that population. So let me step back for a second. Okay. Right now where we're heading in inference and statistics, we're going to look at some claim. M&M says 23% of my M&Ms are blue, okay, in the package. We open up a package and we get 2 blue out of, 40, however many are in a little package. And we think, I don't think that their claim is right. Okay, we're looking at the claims of the population and seeing if we have convincing evidence or not that that claim is true. Okay, so when we're looking at this sampling distribution, okay, we're going to take the claim, which in this case, this was the red and blue chips. 50% the teacher said are red. So here is a graph of our population. This is called the population's distribution. From that population, because we don't have time to do every single sample, really, but if we did, if we could take every single sample, we would get to the true population parameter. We're going to take as many samples as we can. We need to take several samples because one, we've already learned the variability could mean that that may not be accurate. So we need to take many samples of the same size from this population. So that's where you see now the next part in green. This is our sample data. We've taken, and this dots here means it just keeps going. We've added multiples here, okay, multiple samples, and we take each of those proportions, all right, p-hats, and we plotted all of those, and that gives us the distribution of the sampling the statistic taken from every single sample. Okay, and then that's what's in red. Okay, we have that there. Okay, so we take our population, we take many samples of the same size from that same population, we take a statistic of those samples, and we plot those statistics onto this graph, and we get a shape, we get an understanding of what's probable for our population parameter. Okay, all right, and we talked about these, so I'm going to move on. Let me come back, and we talked about then it's an unbiased estimator if it equals that. Okay, if it equals what it's estimating, then it's called it's unbiased. Okay, I'm going to go through these. We did all this and found that the range was not an unbiased estimator, but the mean was, okay? And also we found that the larger our sample size, the less variability that we saw, and this is what we looked at yesterday. So we came down to the conclusion that sample size is the most important factor here. It doesn't care about the population size. Oh great, my lights just went out. Okay, sample size is more important than population size, and so remembering that, this is what's going to head us into into Thursday and Friday. Hang on, I'm going to turn my lights back on so I can see. Sorry about that. The automatic lights of the classroom go off when I'm in this corner. It doesn't see movement. Okay. All right. So continuing on. Okay. This is where we left off yesterday. We found that P, the proportion of the population proportion, can be estimated well with P hat. It's an unbiased estimator. Same thing. X bar will be an unbiased estimator of our mu when we take many, many samples of this. Okay, I love this diagram though. This is new now. I want you to think about this. Targets, okay? You know, if we were shooting, we want to get into the center. That is our target. That's our goal, okay? But if we have an estimator that has high bias, remember that's not equal to, so it's high bias, it's going to miss the mark. This one has low variability though, because it's all missing the mark in the same spot, but it's not hitting the mark. Okay, this is high bias and low variability. The estimator over here has low bias because the center of it is the center of the target. So we're around the center, but we have high variability, so it's spread out around the center. Letter C, we miss the mark altogether, and so this is high bias, high variability. Okay, way off. This target right here is where we want to be, okay? We want to get to this, I've put it in red here, okay? Where we have low variability and no bias, okay? And this is how we want our estimators to be, because then we get on target and what we're saying about the population will be more likely true, okay? More likely accurate. So this is what we're talking about. Bias means, and I want you to see the difference here, bias means that our sample statistics do not center on the population parameter. So this one has bias, and there's nothing centered around what we want it to do. Okay, our estimates are just plain old not accurate at all, way off. High variability, though, means that repeated samples do not give very similar results. Okay, so we're really high variability and we don't have similar results, so we're not very precise. You wouldn't get very many points in a game like this, or shooting your arrows and getting points, if you couldn't get to the middle of the target very often. This is where we want to be. So ideally, this is what we want, is that low variability and unbiased estimator. So there is an exam tip that is given to you in your textbook, and I added it in here because I think it's pretty important. We have to be careful how we use accurate and precise. Accurate means being correct, like being on around it. Okay, accurate. Precise, so if we're around the estimator, I mean around the true proportion or the true mean, and we're around it, we are there, but we're accurate, but we're just not very precise. Okay, the one that target that was way off base here, this is not accurate and this is not precise at all. Okay, here we have accurate and precise. This is, we don't want to say we're not accurate, we're just not precise. Accurate means we're wrong with it. So our estimator is not going to be wrong. It's just going to be, what we want to say here is increasing the sample size would make an estimate more precise, not more accurate, more precise. We would get in onto the detail quickly. And so they say if that gets you confused and you don't know which words to use, then explain what you mean without saying some of these words, because they do mark you off if you've misspoken. Okay? All right. I told you notes were short today, so that's what it is there. We're going to go to the one worksheet we did not get to yesterday, which is this one. Day 1, 7-1, day 1. Okay? What I'd like for you to do is to take these, this is a sample test scores, 4 scores from a test. Make a dot plot of the population. So this is your population. Make a dot plot of that. Pick any 2 of the scores that you want and get the mean of that particular sample. Then figure out all possible samples of size 2 and do the means of all of those. And make a dot plot using the means you found in number 3. You did a lot of this in your homework last night, so I'm hoping this will go quickly for you. What I want you to then do is say, what is the mean of the population? So come back up to your population and calculate the mean and label that on your dot plot. What you're going to put in Edpuzzle now is you're going to put in not all of these answers, just after you finish number 5, what do you notice about the mean of the population and your dot plot? How does that mean fit in with your dot plot of the sample means that you have been plotting. Okay? All right, go take some time to finish that, and we'll come back and look at the answers. Okay, we're back. That's fast. I'm not going anywhere. You guys are. Make a dot plot of the population distribution. Okay, this is just one individual score of 90, one individual score of 80 from the population, right? This is just happens to pick 60 and 70. You could have picked any two, whatever your two were, your X, but remember you put X bar because would be one of the sample means. So we're trying to work on using our notation properly. 60 and 70, here we go, all of the possible ways and all the possible means. And then you plotted those. Here's your sampling distribution of these X bars. And then you should see that the mean of the population is 75, and look at that. Look at that population mean. Hot diggity dog. It's right smack dab in the middle of my graph where it should be. The mean of my X bars, the mean of the means is going to be my unbiased estimator. Okay, really, really cool. Now we're not doing the second page of this worksheet because we did this in class. This is the Jenna problem that I did in class with you. However, it is there if you wish to take notes on it from the notes that we did yesterday. Okay, let's go to day 2. Again, we will not be doing the first page of lesson 7.1 day 2. We're going to skip that and come down. I just want you to do 1, 2, and 3 here on the back of this page. Okay, and I would like for you to put your answers to these 3 questions in Edpuzzle, and then we're going to come back and look at the answers, and you'll be done for the day. So take a look at this. This is interesting because it's looking at median. Remember yesterday we looked at range to see if it's a possible unbiased estimator. We found it really was not an unbiased estimator. Let's see if we can figure out what happens with median. Okay, this one's asking you to look at the sample median. So remember, median is where 50% of the data is below it and above it. So you got to figure out where 50% lies to find the median of the population. And then look at the median of our samples of the sample median. And again, there's no symbol here for this because we're not using sample median very often. So they don't make a special symbol for it in stats. It's just called the sample median. And then what do you think would happen if we took sample size 20 instead of 10, like this was taken size 10? And then what is the shape of the distribution of the sample median? Not the population distribution, but the sample distribution, sampling distribution, I should say. All right, go do it. All right, welcome back. Check your understanding. One last thing we're going to do today. If you go to the first graph, you will see the median of the population is 75, whereas the median of the samples is 73.5. So since they are not the same, this is not an unbiased estimator, not good. So we could not use the median to estimate. That's where we're going to stick with our good friends, means and proportions that do work. Okay, suppose you had taken 20 instead of 10 as your size for your samples. It's the same though, same as everything. Variability is going to decrease because that sample size is increasing, just like it would for the means and the proportions. And then the last question, hopefully, that's about taking us all the way back to chapter 1, I believe it is, with socks, but just the shape here, it is skewed left, as we can see it's skewing left, with a single peak between 75 and 77.5. You could have said unimodal if you wish. All right, you're going to have a good holiday tomorrow, and then Thursday when we come back, we're going to start section 7.2, but if you have any questions, email me as you're working on the homework or something, and then when I can, with my one eye, I'll look and get back to you, and I'll have a good holiday, really good day off, and I'll see you Thursday.